In this lecture, we will see what is uniqueness theorem in electrostatics, and we will also try to prove this. In our previous lectures, we have seen two equations. The first one was the Poisson's equation, del square V is equal to minus rho by epsilon naught, and del square V is equal to 0 for the case when there is no sources. Now, of course, this is a special case of Poisson's equation. Now, there is a uniqueness theorem which exists and states that if there is a solution to Poisson's equation, of which this Laplace equation is a special case, and that solution satisfies this equation as well as the boundary conditions, then this solution is a unique solution and no other solution exists. Means it does not matter how we get to this solution. If we get to the solution that satisfies this equation as well as the boundary conditions, then that solution is a unique solution, and the way or method by which we got that solution does not matter. Even if we somehow guess the right solution, then it will be the correct one, and we will just have to show that this satisfies the equation and the boundary conditions. And one of the method called method of images is based on this uniqueness theorem. Now we will try to prove this theorem by contradiction. Let us say that there is this volume tau, and this volume tau is spread, let us say it can spread to even infinity also, that is, it can cover the whole universe, and its surface is S naught. This surface is S naught. This bounding surface of this volume is this S naught, and these are the normals, surface normals A. Now this volume inside, it may have many conductors, conductor 1, conductor 2, conductor 3, and these may be charged or may not be charged, and for them the normal will be like this. So this is S1 surface, S1 surface for conductor 1, S2 surface, S3 surface, and so on, Sn surface. And these, as I've told, these can be charged conductors also with charges on their surface. As we know that in electrostatics, charge comes to the surface of the conductor. It does not reside inside the conductor. So we know the potentials of these conductors or surface, because this is an equipotential with, let us say, potential V1. This is an equipotential with potential V2, similarly V3 and V and so on. And we also say that we know the potential of this bounding surface. Now we assume that instead of this unique solution, there are two solutions which satisfies the Poisson's equation as well as the boundary conditions. Let us say these solutions are V1 and V2. So it implies that del square V1 is equal to minus rho by epsilon naught, and del square V2 is equal to minus rho by epsilon naught. And since these also satisfy the boundary condition, so we know that the potential difference Vd, which is equal to V1 minus V2, it is equal to 0 for the surfaces for which we know the potentials, because on those surfaces V1 will also be equal to the same potential and V2 will also be equal to the same given potential of the boundary. So at S0, S1, S2 and so on, Sn, this is going to be 0. The value of this potential Vd is going to be 0. That is, del square Vd is going to be del square V1 minus del square V2 equals to 0. That is, del square Vd equal to 0. Now we have seen so many times this formula where we take the divergence of a vector multiplied by a scalar, and it is given as del f dot a plus a dot or f into del dot a. This formula we have seen so many times. Now what we will do, we will write f is equal to this Vd, the potential difference between these two solutions, or the difference between these two solutions, and the vector a is simply the gradient of this difference in the solutions. So gradient or divergence of this Vd del Vd will be equal to simply del Vd dot del Vd plus Vd del dot del Vd, or equals to del of Vd square plus Vd del square Vd. Now we have seen in the previous slide that this is equal to 0, del square Vd is equal to 0. So we see that del dot Vd del Vd equals to del of Vd square, its magnitude square. Now we will integrate this along the whole volume, given volume. So del dot Vd del Vd along the whole volume tau should be equal to integration of this del Vd square along the whole volume tau. Now we will utilize the Gauss divergence theorem, which we have seen in our previous lectures, and convert this volume to the surface, because as of now we will have to evaluate at every point of this volume. However, if I convert this to surface integral, then I will have to just integrate over the bounding surface only. So it implies that I can write using Gauss divergence theorem that along the bounding surface, this Vd del Vd dot an ds should be equal to del Vd square dv. Now, since we are going to integrate over the surface, and this surface, it may extend to infinity also, that is, the radius of this surface may tend to infinity. So we can see that to evaluate this integral Vd del Vd dot an ds, we may need to evaluate when r tends to infinity. Now we know that the potential V1 and V2, they are at least going to fall with this rate, because we have seen the potential due to a point charge or a charge, some configuration of charge, the minimum rate of fall is going to be 1 by r. For a dipole, it may be 1 by r squared, and some other cases it will be again faster than that, given that the charge is not going to have any infinite extent like it is everywhere. So in a normal, simple, practical scenario, this V1 and V2, these are going to fall with this rate minimum. It can be more than that also, that the fall may be more steeper. So we know that del of V1 and del of V2 are going to at least fall at a rate of 1 by r squared. So you see that Vd del Vd, it is going to fall with a rate of at least 1 by r cube. Now ds, it is just proportional to r squared. So it implies, while we will evaluate this integral on the surface when this r tends to infinity, then this integrand is going to 0 when r tends to infinity. So the LHS of this equation is going to 0 when we are going to bound the whole universe. So it implies that this del Vd magnitude square dv is equal to 0 over the whole volume tau. Now we know that this del Vd square is not equal to, or it is not smaller than 0, that is, it is never going to be negative. So it implies that this integral, if it is going to be 0 everywhere in the volume, then the only possibility is that this del Vd square is equal to 0, or del Vd is equal to 0. So it will be satisfied if and only if this is satisfied everywhere. Means this gradient should vanish everywhere at all points in the volume, as we have seen that this Vd is equal to V1 minus V2 equals to 0 on the boundary. Now, since gradient of this Vd is 0 everywhere, it implies Vd is not going to change anywhere. Since its gradient is 0, so there is not going to be any change. So it implies the Vd value is not going to change anywhere, and if we somehow find the value of this Vd, it will remain the same value everywhere in this volume. Now we have found that this Vd is equal to 0 on the boundary. So it implies that Vd is equal to 0 everywhere in the volume as well as on the surfaces. So it implies V1 minus V2 is equal to 0. It implies the solution is same for both cases. So we have shown that this is the only one possible solution, and there cannot be any more than one solution which are going to satisfy the Poisson's or the Laplace equation and the given boundary conditions. So hence we have proved the uniqueness theorem in electrostatics. And of course it is valid in other phenomena where we have equations of the form of Poisson's equation or the Laplace equation. There will be so many other phenomena where we will find similar equations, and as Feynman has said, similar equations have similar solutions. So this uniqueness theorem is going to be followed everywhere in such cases also. So if you find that this lecture is helpful to you, then please share and subscribe our YouTube channel, and also join our Telegram group whose link is given in the description of this video.